What if everything you know about matter has a mirror that feels familiar, yet has never truly touched your world? If you find yourself drawn to quiet questions like this, about the hidden structure of reality and the gentle mysteries beneath everyday physics, you are warmly welcome here. A soft like or a calm subscription helps keep this small corner of science alive, but only if it feels right to you. Antimatter begins its story in a place that feels almost ordinary, because it is built from the same fundamental idea as matter itself. In the early 20th century, physicists began to realize that the universe was not only made of solid objects and invisible forces, but of patterns that repeat with remarkable precision. At the heart of everything we call matter are particles, tiny excitations in quantum fields that stretch everywhere, quietly present even in empty space. Electrons, protons, and neutrons are not little beads floating in a void. They are localized ripples, stable vibrations in these fields, held together by the rules of quantum mechanics and relativity. Antimatter is made of particles that mirror these ripples almost perfectly. An antimatter electron, called a positron, has the same mass as an electron, the same spin, the same ability to orbit an atomic nucleus. The difference is subtle but profound. Its electric charge is opposite. Where an electron carries a negative charge, the positron carries a positive one. This reversal is not cosmetic. It changes how the particle interacts with electromagnetic fields, how it bends in magnetic traps, and how it behaves when it encounters ordinary matter. This idea emerged naturally from mathematics, not imagination. In 1928, Paul Dirac was working to unify quantum mechanics with Einstein's special relativity. His equation described electrons with stunning accuracy, but it contained solutions that puzzled him. The math allowed for electrons with negative energy, states that did not seem to exist in the real world. Rather than discard these solutions, Dirac followed them carefully. He realized that the equation was quietly predicting a new kind of particle, identical to the electron in every measurable way except for charge. This was not philosophy or speculation. It was a necessary consequence of the structure of the equation itself. When the positron was discovered experimentally a few years later in cosmic ray tracks by Carl Anderson, antimatter moved from abstraction into reality. The tracks curved the wrong way in a magnetic field, leaving a delicate signature in cloud chambers. Antimatter was no longer a theoretical curiosity. It was something nature produced on its own, high above Earth, when energetic particles from space collided with the atmosphere. To understand what antimatter is made of, it helps to slow down and look at matter first. A hydrogen atom consists of a proton and an electron. The proton itself is made of quarks, held together by gluons through the strong nuclear force. In antimatter, each of these components has an antiparticle. An antiproton is made of antiquarks, bound by the same strong force, mediated by the same gluons. The gluons do not change, because they carry color charge rather than electric charge, and the strong interaction is symmetric in this way. What changes are the quarks themselves. Each quark is replaced by an antiquark with opposite quantum numbers. An antihydrogen atom, therefore, consists of an antiproton orbited by a positron. Structurally, it is astonishingly familiar. It has energy levels, spectral lines, and quantum transitions that mirror hydrogen almost exactly. Experiments at CERN have trapped antihydrogen atoms long enough to study their behavior, comparing them with ordinary hydrogen to extraordinary precision. So far, Every measurement suggests that the laws of physics treat matter and antimatter with near-perfect symmetry. This symmetry is known as CPT symmetry, a fundamental principle of modern physics. It states that if you reverse charge, parity, and time simultaneously, the laws of physics remain unchanged. Antimatter fits naturally into this framework. It is not an exotic substance glued together by strange rules. It is built from the same quantum fields, following the same equations, existing as the mirror solutions those equations allow. And yet, despite this deep symmetry, antimatter feels elusive. The reason is not what antimatter is made of, but what happens when it meets matter. When a particle encounters its antiparticle, they annihilate. This word sounds violent, but the process is precise and elegant. Their mass is converted into energy, often in the form of gamma rays, according to Einstein's equation E equals mc squared. Nothing mystical occurs. Conservation laws are obeyed exactly. Energy, momentum, and quantum numbers balance perfectly. The particles vanish not because they are unstable, but because they have completed a transformation into another form of the same underlying reality. This annihilation is why antimatter is so rare around us. The universe we inhabit is overwhelmingly made of matter. If significant amounts of antimatter existed nearby, the boundaries where matter and antimatter met would glow with intense radiation. Astronomers have searched for such signatures on cosmic scales, and while antimatter is produced in small quantities in energetic environments, large antimatter regions appear to be absent from the observable universe. This absence leads gently to one of the deepest open questions in physics. If matter and antimatter are made symmetrically, why does anything exist at all? The Big Bang should have produced them in equal amounts. Somewhere in the early universe, a slight imbalance occurred, favoring matter by a tiny margin. That margin was enough to build galaxies, stars, planets, and eventually the quiet moment you are experiencing now. But returning to composition, antimatter is not made of anything unfamiliar. A positron is not made of anti-stuff layered differently from an electron. It is an excitation of the same electron field, but with opposite charge. An antiproton is an excitation of the same quark fields, arranged in a configuration that mirrors a proton. The distinction lies in quantum numbers, not substance. Matter and antimatter are two expressions of the same underlying fields, like waves moving in opposite directions across the same calm surface. Even neutrinos, those nearly massless particles that pass through your body in vast numbers each second, may have antiparticles, though their exact nature remains under study. Some theories suggest neutrinos could be their own antiparticles, a possibility explored through experiments searching for neutrinoless double beta decay. If true, this would blur the boundary between matter and antimatter even further, showing that nature sometimes chooses elegance over symmetry. In laboratories, creating antimatter requires energy. Particle accelerators slam particles together at high speeds, converting kinetic energy into mass, producing particle-antiparticle pairs. These pairs are born together as if the universe insists on balance at the moment of creation. Capturing antimatter is delicate work. Magnetic and electric fields are used to hold antiparticles in place, preventing them from touching the walls of their containers, which are made of ordinary matter. These traps are quiet and precise, more like musical instruments than cages, holding charged particles in invisible wells shaped by equations. Despite its reputation, antimatter is not inherently dangerous. A single positron annihilating with an electron releases an amount of energy too small to notice. Even the total antimatter ever produced by humanity would barely warm a cup of tea if fully annihilated. Its danger exists mostly in imagination, amplified by science fiction. In reality, antimatter is fragile, fleeting, and extraordinarily difficult to store in meaningful quantities. There is also a strange intimacy to antimatter. Positrons are used in medical imaging, in a technique called positron emission tomography. In these scans, tiny amounts of antimatter help doctors see inside the living body, revealing metabolic activity with remarkable clarity. Here, antimatter becomes a tool of healing, not destruction, its annihilation translated into information rather than force. When you strip away the drama, antimatter is made of symmetry and mathematics, of balance and reversal. It is made of the same quarks, the same leptons, the same quantum fields that compose everything you know. It exists because the equations describing reality allow it, and because nature follows those equations with quiet consistency. If matter is a melody played in one direction, antimatter is the same melody played in reverse, not louder, not stranger, just different enough to reveal the structure beneath the music. Both arise from the same instrument, the same underlying laws, vibrating gently across space-time. And, as physicists continue to study antimatter with increasing precision, they are not only learning what it is made of, but why the universe chose matter over antimatter in the first place. That answer, still unfolding, may lie in subtle asymmetries, in rare processes that occurred only once, long ago, when the universe was young and hot and expanding rapidly. For now, antimatter remains a quiet reminder that reality is richer than it appears, that even the most solid things have mirrors written into their foundations, and that the universe often reveals its deepest truths not through spectacle, but through symmetry, patience, and careful listening to what the equations have been saying all along. As the understanding of antimatter deepened, physicists began to notice something quietly unsettling. If antimatter is made of the same ingredients as matter, arranged with such precision and symmetry, then its near absence is not a trivial detail. It is a clue. And, like many clues in physics, it whispers rather than shouts. In the early universe, when temperatures were unimaginably high, energy condensed into particles and antiparticles constantly. Space itself behaved like a restless sea, with matter and antimatter appearing and disappearing in pairs. This was not chaos. It was equilibrium. For every particle that formed, an antiparticle formed alongside it, their existence balanced by the same laws that still govern particle accelerators today. In that early moment, antimatter was not rare. It was everywhere, woven into the fabric of the newborn cosmos. As the universe expanded and cooled, these pairs met and annihilated, returning their mass to radiation. Most of the matter and antimatter vanished this way, leaving behind a universe filled mostly with light. But something subtle happened. For reasons still being studied, a small excess of matter remained. Not much. Perhaps one extra matter particle for every billion particle-antiparticle pairs. That tiny imbalance was enough. When annihilation ended, those few surviving particles became everything solid that would ever exist. Understanding what antimatter is made of does not fully explain why it lost this ancient competition, but it reveals how close the contest was. Matter and antimatter were born equal in structure, equal in mass, equal in complexity. The universe did not prefer matter because it was simpler or more stable. it preferred matter because of a faint asymmetry hidden deep within the laws themselves. This asymmetry shows up in certain particle decays, particularly involving particles called mesons. In experiments, physicists have observed that some particles and their antiparticles decay at slightly different rates. This phenomenon, known as CP violation, hints that nature treats matter and antimatter with almost perfect fairness, but not quite. The difference is small, almost tender in scale, but its consequences are cosmic. Antimatter, then, is made of the same fundamental building blocks as matter, but its story diverges at the level of behavior rather than composition. It is not missing something. It is not unstable by default. It simply follows rules that are almost the same, but gently tilted. At the level of fields, this becomes even clearer. In quantum field theory, particles are excitations of underlying fields that permeate all of space. The electron field gives rise to electrons and positrons alike. The quark fields give rise to quarks and antiquarks. The fields themselves do not care which excitation you observe. They allow both. They demand both. Antimatter is not an afterthought. It is built into the framework from the beginning. This perspective softens the boundary between matter and antimatter. Instead of imagining two kinds of substance, it becomes easier to imagine one continuous foundation expressing itself in complementary ways. Like peaks and valleys in the same landscape, matter and antimatter emerge from the same terrain, shaped by the same underlying geometry. Even gravity appears to treat antimatter the same way. Recent experiments have begun to test how antimatter responds to Earth's gravitational field. The expectation, based on general relativity, is that antimatter falls downward just like matter. Early results support this view. Antimatter does not float upward or behave strangely in gravity's presence. It participates in space-time curvature the same way, adding its mass and energy to the quiet shaping of geometry. This tells us something important. Antimatter is not a violation of the universe's logic. It is a confirmation of it. The same principles that allow stars to shine and atoms to bond also allow antimatter to exist, briefly or rarely, wherever enough energy gathers. And in fact, antimatter is constantly being created, even now. High-energy cosmic rays strike Earth's atmosphere, producing showers of particles and antiparticles. Lightning storms can generate positrons. Certain radioactive decays release them. The universe has never stopped making antimatter. It simply does not let it linger. When physicists describe antimatter as rare, they are really describing its environment. In a universe dominated by matter, antimatter has few safe places to exist. But in controlled conditions, when carefully isolated, it behaves with calm predictability. Antihydrogen atoms form quietly. Positrons settle into stable orbits around antiprotons. Spectral lines emerge exactly where theory says they should. There is a quiet beauty in this. Antimatter is not exotic in behavior. It is exotic only in context. It is like a familiar language spoken in a place where no one else speaks it. The words are the same. The grammar is the same. Only the surroundings are different. This realization has shifted how physicists think about the universe. Instead of asking why antimatter exists, they ask why matter dominates. Instead of seeing antimatter as strange, they see it as essential, a necessary counterpart that reveals symmetry by contrast. In this way, antimatter becomes a lens. Through it, physicists test the deepest assumptions of their theories. They compare hydrogen and antihydrogen with extraordinary care, looking for differences so small they would escape almost any other measurement. They listen for deviations that might signal new physics, new fields, or hidden dimensions of reality. So far, the mirror remains faithful. Matter and antimatter continue to match each other with uncanny precision, and that precision itself is a message. It suggests that the universe is built on principles that value balance, even when balance is broken just enough to allow existence. Antimatter is made of the same quiet ingredients that make you, the same particles dancing in fields that stretch across the cosmos. Its difference lies not in substance, but in sign, in orientation, in a subtle reversal that mathematics permits and reality confirms. And as the universe continues its slow expansion, antimatter remains a reminder that what exists does so by the smallest of margins, that reality is shaped not only by what is present, but by what almost was, and that sometimes the most important stories in physics are written in differences so small they can only be seen by listening very carefully, over long periods of time, to the soft, consistent voice of nature itself. There is something reassuring in realizing that antimatter is not an entirely separate category of existence. When you first hear the word, it can sound like the universe invented a second kind of substance just to be strange. But once you sit with it for a moment, antimatter starts to feel more like a natural extension of ideas you already know. It follows the same rules, fits into the same equations, and responds to the same forces. It is not a rebellion against physics. It is physics being thorough. A helpful way to think about this is to imagine the basic properties of particles as a set of labels they carry with them. Electric charge is one of those labels. Spin is another. There are others too, quieter ones, like lepton number or baryon number, which keep track of how particles can be created or destroyed. An antiparticle carries the same labels as its particle partner, but with certain signs flipped. Not all of them, just the ones that matter for symmetry. This is why antimatter behaves so predictably. It is not missing information. It is simply wearing the same information with opposite orientation. When an electron and a positron meet, they recognize each other instantly. Their opposite charges pull them together, and when they overlap, the rules of quantum fields allow them to transform. The electron field and its corresponding antiparticle excitation cancel in a precise way, releasing energy as light. Nothing is lost. The fields remain. The energy continues onward. This is not destruction in the dramatic sense. It is more like two ripples meeting on a pond and flattening back into the surface they came from. This idea helps explain why antimatter is so difficult to keep around. The universe, as it exists now, is filled with electrons, protons, and neutrons. Any antiparticle introduced into this environment is surrounded by partners eager to complete that cancellation. To preserve antimatter, physicists have to isolate it using clever arrangements of electric and magnetic fields, holding it in place without letting it touch anything solid. Even then, it survives only briefly. Not because it is unstable, but because its surroundings are overwhelmingly incompatible. What often surprises people new to this topic is how ordinary antimatter feels once you remove it from those surroundings. In a vacuum, guided by fields, antiparticles behave calmly. They move, they orbit, they respond to forces exactly as expected. There is no sense of volatility or chaos. Antimatter does not flicker or hiss. It simply exists quietly until something else gets in the way. This calmness is one of the reasons physicists are so interested in studying it carefully. If matter and antimatter are made of the same things, then any difference in their behavior could point to new physics. Even the smallest deviation could reveal something fundamental about why the universe looks the way it does. This is why experiments comparing hydrogen and antihydrogen are done with such patience. Researchers are not looking for dramatic effects. They are looking for tiny mismatches, shifts so small they might only appear after years of careful listening. So far, the universe has been remarkably consistent. Antihydrogen emits and absorbs light at nearly the same frequencies as hydrogen. Its internal structure appears identical. This reinforces the idea that antimatter is not an exotic ingredient, but a faithful counterpart. It can also be helpful to zoom out and think about why nature would include antimatter at all. From a modern perspective, it is almost unavoidable. Once you combine quantum mechanics with relativity, antiparticles emerge naturally. They are not added later. They fall out of the mathematics as soon as you demand consistency. In that sense, antimatter is less a feature of the universe and more a feature of the rules we use to describe it. This can feel abstract at first, but there is a quiet comfort in it. The universe is not improvising wildly. It is following a set of deep principles that allow certain patterns and forbid others. Antimatter exists because symmetry exists, and symmetry exists because it keeps the rules coherent. Even when that symmetry is slightly broken, as it appears to be in the early universe, the break is delicate. It does not shatter the structure. It nudges it just enough to allow something new to persist. Matter remains. Antimatter fades. But both were necessary to reach this outcome. Thinking about antimatter this way can gently shift how you see matter itself. The solidity of the world becomes less absolute. What feels stable and permanent is revealed as the result of balances and cancellations that could have gone another way. The atoms in your body exist because of a small preference written into the laws of physics, a preference so slight it took decades of experiments to even notice it. And yet, here it is, shaping everything. Antimatter, then, is made of the same quiet ingredients as matter, but it carries a reminder with it. Reality is not just about what exists now, but about what was possible at the beginning. It is about paths not taken, balances almost perfect, and symmetries that still echo through every particle interaction happening around us, even in moments that feel still and simple. There is another layer to antimatter that often feels less intimidating once you see it clearly, and that is the role it plays in everyday physics without ever announcing itself. Even if you have never thought about antimatter before, it has already been part of your story. Every time certain types of radioactive atoms decay, they release positrons. These positrons travel a short distance, meet electrons, and quietly convert their mass into light. This happens naturally, gently, without spectacle, all around us. What makes this interesting is how normal it all is. The equations that describe these processes are the same ones that describe electricity, magnetism, and light. Antimatter does not require a special chapter in physics textbooks because it is woven into the same chapter as everything else. It simply occupies a different line in the same set of solutions. If you imagine the universe as a vast instruction manual written in mathematics, antimatter is not a footnote. It is printed right next to matter, using the same ink. Once you see that, the question of what antimatter is made of starts to feel less mysterious. It is made of the same rules being followed completely. Even the word antimatter can be misleading. It suggests opposition, as if antimatter were somehow hostile to matter. But in physics, the word anti usually just means opposite in a very specific technical sense. Antiparticles are not enemies of particles. They are partners. They complete the picture. This partnership shows up beautifully in how particles are created. Whenever enough energy is concentrated in a small region of space, particle-antiparticle pairs can emerge. This is not optional. Conservation laws demand it. Charge must balance. Quantum numbers must add up correctly. Nature insists on fairness at the moment of creation, even if that fairness does not persist forever. There is something quietly elegant about that insistence. It suggests that the universe is careful with its bookkeeping. Nothing appears alone. Everything is accounted for. Matter may dominate now, but it did not arrive unaccompanied. For someone new to this topic, it can help to pause here and notice how little drama is actually involved. Antimatter does not challenge your intuition about cause and effect. It does not violate common sense once you understand the framework. It simply extends familiar ideas into a more complete form. And that completeness matters. Without antimatter, many of the most successful theories in physics would fall apart. The equations would be inconsistent. Predictions would fail. The existence of antimatter is one of the reasons physicists trust these theories so deeply. It is not an extra feature added to match experiments. It was predicted before it was observed, which is one of the quiet triumphs of theoretical physics. As experiments continue, physicists are beginning to ask more refined questions. Not just what antimatter is made of, but how precisely it mirrors matter. Does antimatter respond to gravity exactly the same way over long periods of time? Are there tiny differences in how its internal states evolve? Could these differences help explain the matter-dominated universe? These questions are approached slowly, carefully, with patience. Antimatter does not reveal itself easily, and it rewards restraint more than force. The best experiments are the ones that disturb it as little as possible, allowing it to behave naturally within carefully shaped fields. All of this reinforces a gentle truth. Antimatter is not a symbol of destruction or danger. It is a symbol of symmetry, of balance, of the universe's tendency to explore every possibility allowed by its rules. It exists because it can exist, and because the laws permit no other option. When you look at it this way, antimatter becomes less of a curiosity and more of a companion concept. It walks alongside matter, illuminating its structure by contrast. It reminds us that what feels solid and obvious is often the result of deeper patterns playing out quietly beneath the surface. And the more you become familiar with those patterns, the more the universe begins to feel not stranger, but more coherent. Like a story that seemed confusing at first, but slowly reveals its logic as you read on, one calm page at a time. As you spend more time with this idea, something subtle begins to happen. Antimatter stops feeling like a special case and starts feeling like a quiet confirmation that the universe is internally consistent. It is as though nature double-checked its work and left the evidence behind, not hidden, just rarely encountered. One of the most grounding things to understand is that antimatter does not live in a separate realm. It is not waiting in another universe or behind some invisible barrier. It exists in the same space as everything else, the same vacuum, the same background fields. The only reason it feels distant is because it does not survive long in an environment like ours. But its short lifetime is not a weakness. It is a consequence of compatibility. If you imagine trying to preserve a snowflake in a warm room, its disappearance would not mean the snowflake was poorly made. It would simply mean the environment was not suited to it. Antimatter is similar. In a matter-dominated universe, it melts almost immediately into light. This perspective also helps when thinking about how antimatter is studied. Physicists are not chasing something volatile or unpredictable. They are creating conditions where antimatter can be briefly comfortable. Magnetic traps act like invisible containers, shaped carefully so that charged antiparticles never touch the walls. Inside these traps, antimatter behaves calmly enough to be measured, observed, and compared. Those comparisons are deeply reassuring. The more carefully matter and antimatter are examined side by side, the more they resemble each other. Their masses match. Their internal energy levels align. Their behavior under forces mirrors almost perfectly. This tells us that the universe is not biased in its construction. The bias came later, gently, subtly, in the unfolding of time. For someone new to this, it can be comforting to know that you do not need to imagine antimatter as something alien. It is not made of negative mass or inverted substance. It is not shadow matter. It is the same matter, seen through a different sign convention. The difference is real, but it is precise, mathematical, and limited. This precision is part of what makes physics feel so calm at its deepest level. Even phenomena that sound dramatic are governed by rules that are patient and exact. Antimatter annihilation is not an explosion in the everyday sense. It is a conversion, clean and efficient, following equations that leave no ambiguity behind. And those equations do not care where you are in the universe. The same processes that create antimatter in particle accelerators on Earth also occur naturally near pulsars, supernovae, and black holes. Wherever energy becomes concentrated, the universe quietly explores the possibility of particles and antiparticles emerging together. This universality matters. It means antimatter is not a laboratory curiosity. It is part of the universe's normal behavior. Even if we rarely see it lingering, it is continuously being created and destroyed across cosmic scales, woven into high-energy environments far from human observation. As your familiarity grows, you may notice that the real mystery shifts. Instead of asking what antimatter is made of, you start asking why matter feels so dominant in your everyday experience. The answer is not that antimatter lost some fundamental contest of strength. It lost by a numerical accident so small it almost feels like a rounding error in the early universe. That tiny imbalance allowed matter to remain when everything else annihilated away. And because antimatter shares the same composition, that imbalance did not need to be large. It did not need to rewrite the laws of physics. It only needed to tilt them slightly. This tilt is still being studied. Physicists build experiments designed to detect differences so small they border on silence. They look at how certain particles decay. They measure tiny asymmetries. They test whether antimatter drifts downward in gravity at precisely the same rate as matter. Each result, even when it confirms expectations, sharpens our understanding. For someone just beginning to explore this, it is worth appreciating how slow and careful this process is. There are no sudden revelations. There are no dramatic breakthroughs announced every year. Instead, there is a gradual tightening of certainty, a narrowing of possibilities, a growing confidence that the picture we have is both incomplete and remarkably accurate. Antimatter sits at the center of this process. It is both familiar and revealing. It reassures us that our theories are sound, while reminding us that something subtle remains unexplained. And perhaps that is why antimatter holds such a quiet fascination. It is not what it is made of that feels mysterious. It is what its existence implies, that the universe could have been different, that symmetry was almost perfect, that what exists now does so because of the smallest of preferences, written into the laws of nature at the very beginning. As you let that idea settle, the world around you does not feel less real. If anything, it feels more delicate, more precise, built not from certainty, but from balance, and from differences so small they require patience and curiosity to notice at all. And in that way, antimatter becomes less of an object and more of a perspective. A reminder that reality often reveals itself not through what is abundant, but through what is rare, fleeting, and just barely allowed to remain. As this picture continues to settle in, it becomes easier to notice how antimatter quietly supports one of the most important ideas in modern science: the idea that nature is not arbitrary. The universe does not choose its ingredients randomly. It allows only what fits together without contradiction. Antimatter fits so cleanly that once it was predicted, its discovery felt almost inevitable. For someone new to this, it can be helpful to step back and think about how little extra machinery is needed to include antimatter. There is no separate set of forces just for it. No new dimensions added only to keep it stable. The same electromagnetic force that binds electrons to nuclei also governs how positrons move. The same strong force that holds protons together also holds antiprotons together. Nothing special has to be invented. This simplicity is part of what physicists mean when they talk about elegance. Antimatter does not complicate the universe. It completes it. You can see this completion most clearly in how conservation laws work. These laws are not suggestions. They are deep constraints that shape every interaction. Charge must be conserved. Energy must be conserved. Certain quantum numbers must balance. Antimatter exists because these rules demand symmetry at a fundamental level. Without antiparticles, the bookkeeping would fail. That bookkeeping especially visible in particle creation. When energy transforms into mass, it does so in pairs. The universe does not allow a lone charged particle to appear from nothing. It insists on balance. This insistence is not philosophical, it is mathematical, and antimatter is the natural outcome. As this becomes more familiar, the idea of annihilation also changes its tone. Instead of sounding like destruction, it begins to feel like closure. Two complementary excitations meet, and the system returns to a simpler state. Light carries the energy onward, spreading it through space. Nothing dramatic remains, just radiation moving at the speed of causality, obeying the same rules it always has. This way of seeing things can gently reshape how you think about matter itself. Matter is not permanent in the way it feels. It is stable only because certain conditions persist. Change the conditions, and matter transforms, just as antimatter does. The universe is not built from unchanging blocks, but from patterns that last as long as the rules allow them to. Antimatter highlights this beautifully. It exists long enough to be measured, studied, and understood, then it fades back into the background it came from. In doing so, it reminds us that what feels solid is often just a long-lived process. There is also something humbling about how carefully physicists must work with antimatter. It resists haste. It cannot be rushed or forced. It demands precision, patience, and respect for the underlying rules. In return, it offers clarity. Every successful measurement strengthens confidence in the structure of modern physics. And when something unexpected appears, even a small discrepancy, it is treated with care. Not excitement first, but verification. Because antimatter is not a place for speculation to run free. It is a place where even tiny differences carry enormous meaning. For someone just stepping into this world, it can be reassuring to know that not understanding everything at once is part of the process. Antimatter does not reveal itself in a single insight. It becomes clearer slowly as familiar ideas rearrange themselves into a more complete picture. What starts as a strange concept becomes a quiet companion to matter, walking alongside it through every equation, every interaction, every field. And once you see that companionship, the universe begins to feel less like a collection of odd exceptions and more like a coherent whole, built carefully, patiently, and with a kind of restrained beauty that rewards slow attention. And so antimatter remains, not as a threat or a mystery to be feared, but as a gentle reminder that reality often includes its own reflections, and that understanding deepens not by adding complexity, but by recognizing symmetry where it has always been present. As the idea continues to unfold, it can be grounding to notice how antimatter quietly reinforces something you may already sense about science itself. The deeper you go, the less it feels like a collection of strange facts, and the more it feels like a single, connected way of thinking about the world. Antimatter is not a detour from that path. It is one of the places where the path becomes especially clear. At its heart, antimatter exists because the universe allows information to be expressed in more than one orientation. Quantum fields do not just permit one kind of ripple. They permit pairs of ripples that are related by symmetry. Once you accept that fields are the fundamental layer of reality, particles and antiparticles stop feeling like separate things. They feel like two ways the same underlying structure can move. This is why physicists often speak about particles and antiparticles using the same language. They are described by the same equations, the same constants, the same principles. The only difference is the direction certain properties point. Charge flips sign. Some quantum numbers reverse, but mass remains positive. Spin remains the same. Lifetimes remain comparable. The universe does not create antimatter as an afterthought. It creates it as a natural consequence. For someone new to this, it can be helpful to let go of the idea that antimatter must be rare because it is difficult or unnatural. It is rare because the universe chose matter by a very small margin, long ago, and that choice has echoed forward ever since. But the processes that create antimatter are still perfectly healthy. They still happen whenever conditions allow. In fact, if you could momentarily step outside the calm scale of everyday life and look at the universe through the lens of high energy, antimatter would seem much less unusual. Near violent astrophysical objects, near the edges of black holes, inside jets from active galaxies, particle energies rise so high that matter and antimatter appear together routinely. In those environments, symmetry briefly returns. Creation and annihilation balance again, if only locally and temporarily. This tells you something important. Antimatter is not gone. It is simply suppressed by circumstance. And circumstance in physics is always secondary to rules. The rules themselves are remarkably forgiving. They allow antimatter to exist. They allow it to behave stably. They allow it to form atoms. They allow it to interact with light. They even allow it to participate in chemistry, at least in principle. Antimatter molecules could exist. Antimatter stars could exist. Entire antimatter galaxies could exist if the early universe had tilted slightly differently. This possibility is not fantasy. It is a direct implication of symmetry, and noticing that can soften the way you think about reality. The universe you experience is not the only one permitted by the laws of physics. It is simply the one that happened. Antimatter, then, becomes a kind of fossil from an earlier moment, a trace of the universe's initial balance. By studying it, physicists are not just learning about particles, they are learning about history, about how the universe chose one outcome over another, not dramatically, but quietly, through small asymmetries amplified by time. As research continues, attention has turned toward ever finer details. How exactly do antimatter atoms respond to electromagnetic fields? How stable are their internal transitions? Do their spectra match matter's perfectly, or is there a whisper of difference hiding just beyond current precision? Each of these questions is approached with care, because the answers are not expected to be loud. This is one of the most beautiful aspects of this field. Progress does not come from shock or surprise. It comes from patience, from repetition, from building instruments that can listen to nature with extraordinary sensitivity. And, as someone new to this topic, you do not need to grasp every technical detail to appreciate the shape of the story. What matters is the pattern. Matter and antimatter are made of the same ingredients. They arise from the same fields. They follow the same rules. Their differences are subtle, precise, and deeply informative. Once that pattern settles in, antimatter stops feeling like something separate from you. The electrons in your body have counterparts that behave the same way under reversed charge. The protons in atomic nuclei have mirror versions built from antiquarks, arranged just as carefully. The physics that holds you together is capable of holding antimatter together too, and that realization can be quietly profound. It suggests that the universe is not tailored specifically to what exists now. It is tailored to consistency, to rules that allow multiple outcomes, even if only one persists. Antimatter also invites a gentler kind of curiosity, not the kind that demands answers immediately, but the kind that is content to explore slowly, to notice how each new experiment narrows uncertainty, how each confirmation strengthens confidence, how each unanswered question points not to ignorance, but to opportunity. When physicists speak about the mystery of why there is more matter than antimatter, they are not expressing frustration. They are expressing focus. They know the framework works. They know antimatter fits. What remains is to understand a small but crucial detail, one that shaped everything that followed. And in that sense, antimatter is not an outlier. It is a guidepost. It tells us where to look. It tells us which assumptions to test. It tells us that the universe's deepest secrets are not hidden in chaos, but in symmetry that is almost perfect, but not quite. As you continue to sit with these ideas, the world does not become stranger. It becomes more coherent. The air around you feels less like emptiness and more like a quiet sea of fields. The objects you see feel less like isolated things and more like long-lived patterns. And antimatter feels less like science fiction and more like a natural extension of everything you already know. It is made of the same substance as understanding itself. Careful definitions, balanced equations, gentle reversals, and a universe patient enough to let those ideas unfold slowly, revealing their meaning not all at once but over time to anyone willing to pay attention without rushing. Antimatter also has a way of quietly sharpening ideas that already exist in physics, especially the idea that nothing is truly isolated. Every particle, every interaction is part of a larger web of relationships. Antimatter fits into that web without stretching it or warping it. It slips into place as if it had always been there, which in a sense it has. One of the most grounding realizations is that antimatter does not require new forces to explain it. The electromagnetic force treats positive and negative charge symmetrically. Flip the sign and the equations still hold. The strong force binds quarks and antiquarks with the same strength. Even the weak force, which is responsible for certain kinds of radioactive decay and is famously asymmetric, still allows antimatter to exist cleanly within its rules. The asymmetry shows up not as a failure of antimatter, but as a subtle difference in behavior over time. This distinction matters. Antimatter is not unstable because it is antimatter. It is unstable only when placed next to matter. In isolation, an antiparticle can live as long as its matter counterpart, governed by the same decay channels and probabilities. A positron does not decay on its own. An antiproton can persist indefinitely if nothing disturbs it. This quiet stability often surprises people because it runs counter to the dramatic stories told about antimatter. Those stories usually focus on annihilation, but annihilation is not a property of antimatter alone. It is a relationship. Matter annihilates antimatter just as antimatter annihilates matter. Neither is dominant. Neither wins. The outcome is mutual and exact. There is something almost philosophical in that symmetry. It suggests that destruction in physics is rarely one-sided. It is transformation governed by balance. When mass becomes light, the universe is not losing something. It is changing how that something is expressed. This becomes even clearer when looking at how antimatter appears in equations. In quantum field theory, particles moving forward in time and antiparticles moving backward in time can be described using similar mathematical structures. This does not mean antimatter literally travels backward through time in any everyday sense. But it does reveal how deeply time, symmetry, and particle identity are intertwined in the foundations of physics. These mathematical relationships are not just abstract tricks. They lead directly to predictions that can be tested. They tell physicists what kinds of interactions are allowed, how particles scatter, how forces behave at small scales. Antimatter fits into all of this without strain. It behaves exactly as the framework says it should. And that reliability is part of why antimatter is trusted. In science, trust is not emotional. It is earned through consistency. Antimatter has earned its place by agreeing with theory again and again, across decades of experiments, under increasingly precise conditions. Even when experiments are designed specifically to catch it misbehaving, antimatter remains cooperative. It does not surprise easily, and when it does, the surprises are small, subtle, and deeply interesting rather than disruptive. This makes antimatter a kind of calibration tool for reality. By comparing matter and antimatter, physicists can test whether their understanding is truly symmetric or whether hidden assumptions have slipped in unnoticed. Each successful comparison strengthens confidence that the framework is sound, even if incomplete. The incompleteness is important too. Physics is very clear about what it does not yet know. The reason matter dominates over antimatter is not fully explained. The mechanisms we know, like CP violation, are not quite strong enough on their own to account for the observed imbalance. This gap is not ignored. It is studied carefully with experiments designed to explore exactly where the difference might come from. In this way, antimatter becomes less about what it is made of and more about what it reveals. It reveals that the universe is almost perfectly symmetric, but not entirely. It reveals that tiny effects can have enormous consequences when given enough time. It reveals that the existence of everything familiar rests on details so fine they can be measured only with extraordinary effort. And yet, for all of this depth, antimatter remains approachable as an idea. It does not require mystical language or complicated metaphors. It can be understood as the universe allowing itself to run its equations in both directions, then watching what happens. There is also a quiet humility in how antimatter is handled experimentally. Creating even a small amount requires immense infrastructure, careful design, and patient repetition. Capturing it demands respect for limits. Physicists do not overpower antimatter. They accommodate it. They shape fields gently. They let it settle. They observe without forcing. That approach reflects something deeper about how knowledge progresses. The most fundamental truths are rarely extracted by force. They are revealed by listening, by waiting, by refining questions until nature can answer clearly. Antimatter rewards that kind of attention. It does not announce itself loudly. It reveals itself through consistency, through alignment with theory, through behavior that is calm and predictable when conditions are right. And perhaps that is why antimatter feels less strange the longer it is considered. It aligns with a view of the universe that is orderly, restrained, and deeply logical. A universe that allows mirrors, reversals, and counterparts not as curiosities, but as necessities. In that universe, matter is not privileged because it is better or stronger. It is simply the version that remained. Antimatter is the version that almost did. That near miss is not a failure. It is the reason anything exists at all. Every atom around you carries the imprint of that early imbalance. Every structure, every pattern, every moment owes its existence to the fact that matter and antimatter were almost equal, but not quite. And antimatter, by existing at all, preserves the memory of that moment. It stands as evidence that the universe once stood at a crossroads, with symmetry intact, and chose a path so slightly tilted that it took billions of years to notice. And so antimatter remains woven into the story of reality, not as a threat, not as an anomaly, but as a quiet witness to how carefully the universe balances possibility against outcome, and how much of what feels solid and certain rests on differences so small they can only be appreciated by slowing down and looking closely, with curiosity rather than urgency, at the deep structure beneath everything familiar. Antimatter also carries a quiet lesson about how much of physics is shaped by what cannot be seen directly. No one has ever held antimatter in their hand or watched it sit on a table. Its presence is inferred through traces, through light, through subtle changes in fields and detectors. And yet its reality is unquestioned, because its effects are precise, repeatable, and consistent with everything else that is known. This way of knowing is common in physics. Gravity was understood long before it was measured with instruments. Atoms were accepted before they were imaged. Antimatter fits into that tradition. It was trusted because the universe behaved as if it were there, long before it was confirmed experimentally. That trust was not blind. It was earned through coherence. Once antimatter entered the picture, many other ideas settled into place. The behavior of high-energy radiation made more sense. The structure of quantum field theory became more complete. The idea that empty space is not truly empty gained strength. Space, even in its quietest state, is alive with potential, with fields capable of producing particles and antiparticles whenever conditions allow. This view of space changes how emptiness feels. Instead of nothingness, there is readiness. Instead of absence, there is structure waiting to be expressed. Antimatter emerges from that readiness just as matter does, equally valid, equally permitted. There is something deeply calming about this. The universe does not need special circumstances to be interesting. Its default state already contains richness. Even when nothing obvious is happening, the foundations are there, steady and full of possibility. Antimatter also sharpens the idea that identity in physics is not absolute. What makes an electron is not a tiny tag attached to it, but a collection of properties and relationships. Flip a few of those properties, and the identity shifts smoothly into something else without breaking the rules. This fluidity can feel unfamiliar at first, but it is one of the reasons modern physics is so powerful. It allows nature to explore variations without reinventing itself. This fluidity extends to how particles transform. In high-energy environments, matter becomes antimatter, and antimatter becomes matter with ease. The distinction is not rigid. It is contextual. What matters is that the underlying laws remain intact. There's also a quiet honesty in how physicists talk about antimatter. They do not claim to understand everything. They acknowledge gaps, uncertainties, and open questions. But they also recognize how much has already been clarified. Antimatter is not a mystery because it is confusing. It is a mystery because it points towards something deeper that has not yet been fully uncovered. That depth often lies in time. The universe had a beginning, and antimatter carries information from that beginning. The slight imbalance that favored matter happened once, early, under conditions that cannot be recreated exactly. Experiments today are attempts to listen for echoes of that moment, to detect patterns that survived billions of years of expansion and cooling. This is why antimatter research feels patient. It is not racing toward an answer. It is refining the question. And even without a final explanation, antimatter already enriches the story of existence. It shows that reality is not built on absolutes, but on near balances. That what remains is not always what was favored most strongly, but what survived the longest. In this light, antimatter becomes less about opposition and more about context. Matter dominates not because antimatter failed, but because conditions shifted. Change the conditions, and the roles could reverse. This does not make the universe fragile. It makes it flexible. It shows that the laws of physics are not rigid scripts forcing a single outcome, but frameworks allowing many, with history determining which one unfolds. Antimatter also invites a different kind of wonder. Not the loud kind, built on spectacle, but a quieter appreciation for consistency. For the fact that equations written on paper can describe both what is common and what is rare, what persists and what vanishes quickly with equal clarity. That clarity is one of the most remarkable achievements of science. It allows unfamiliar ideas to feel approachable. It turns what first seems alien into something that fits naturally alongside everything else. Antimatter does this without demanding attention. It does not dominate everyday experience. It does not intrude. It simply exists whenever it is allowed to, as faithfully as matter itself. And in doing so, it leaves behind a gentle impression that the universe is larger than immediate experience, that symmetry runs deeper than appearance, and that understanding often comes not from dramatic discoveries, but from recognizing how quietly different pieces belong to the same whole. Antimatter belongs. It belongs in the equations, in the experiments, in the history of the universe. It belongs as a reminder that what feels inevitable now was once uncertain, and that the reality being experienced is one outcome among many that were possible, shaped by differences so slight they reveal themselves only to careful, sustained attention. And that attention, calm and curious, is often all that is needed to see how even the most unfamiliar ideas can settle into place, becoming part of a larger, coherent picture that feels less like a collection of facts and more like a single, unfolding understanding of how the universe allows itself to exist. Antimatter also quietly reshapes how scale feels in physics. At human scales, the world appears stable, predictable, and one-sided. Matter is everywhere. Antimatter is almost nowhere. But when scale shrinks down toward the fundamental, that imbalance fades. At the level of fields and equations, matter and antimatter are treated with equal seriousness. They are both allowed solutions, both expected outcomes, both present in the deep structure of reality. This contrast between scales is important. It shows how what feels dominant locally does not always reflect what is fundamental globally. The everyday world is shaped by history as much as by law. The laws allow antimatter. History favored matter. Both statements are true at the same time. Physics often works this way. The deepest rules are simple and symmetrical. The world that emerges from them is complex and specific. Antimatter sits exactly at that boundary, where simple rules meet complicated outcomes. There is a quiet elegance in how little additional explanation antimatter requires. Once quantum fields are accepted as the foundation, antiparticles follow naturally. They are not patched in later. They are already there, waiting to be noticed. This is why their discovery felt so satisfying. It was not a surprise so much as a confirmation that the framework was holding together. That sense of structural integrity matters. It gives confidence that the universe is not stitched together from unrelated pieces. Instead, everything appears to grow from the same roots. Antimatter shares those roots completely. Even language reflects this closeness. Physicists rarely speak about antimatter without also speaking about matter. The two concepts are inseparable. One defines the other. Remove antimatter, and matter becomes harder to describe consistently. Remove matter, and antimatter loses its reference point. Together, they form a pair that stabilizes the theory. This pairing also shows up in how experiments are designed. Detectors are built to recognize both particles and antiparticles using the same principles. Tracks curve in opposite directions in magnetic fields. Energy deposits appear in predictable patterns. The same instruments that reveal matter reveal antimatter, with only slight adjustments in interpretation. There is something deeply reassuring about this reuse. It suggests that understanding does not require endless novelty. Often, it requires seeing how familiar tools apply in unfamiliar situations. Antimatter also softens the boundary between existence and non-existence. A particle and an antiparticle can appear from energy and disappear back into it. This does not violate conservation, it honors it. Energy changes form. Fields shift their excitations. The universe remains balanced. This fluidity can feel unsettling at first, but it becomes calming once accepted. It suggests that nothing is ever truly lost. It only changes how it is expressed. Matter and antimatter are temporary shapes taken by something deeper and more persistent. That deeper layer is the network of fields filling space. These fields are always present. They do not come and go. What comes and goes are the excitations, the particles and antiparticles that briefly rise above the background. Antimatter is one such rise, no less legitimate than matter. This perspective can change how the word creation feels. When antimatter is produced in a laboratory, nothing is being conjured from nothing. Energy already present in fields is being reshaped into a new configuration. When antimatter annihilates, that configuration relaxes back into radiation. The universe breathes in and out, but the underlying substance remains. Antimatter fits beautifully into this breathing rhythm. It is part of the inhale and the exhale. It exists in the transition. There's also a subtle lesson here about expectations. Popular culture often frames antimatter as explosive, unstable, or dangerous. Physics reveals something much quieter. Antimatter is delicate. It must be protected from contact. It must be handled gently. It is less like a weapon and more like a rare instrument, useful only when treated with care. This gentleness extends to how knowledge about antimatter grows. Results accumulate slowly. Precision improves incrementally. Confidence builds not through dramatic surprises, but through repeated agreement between theory and observation. That agreement is powerful. It tells us that the mathematical language used to describe reality is not arbitrary. It captures something real and enduring. Antimatter speaks that language fluently. And when differences appear, when matter and antimatter behave just slightly differently under certain conditions, those differences are treasured. They are not flaws. They are clues. They point toward parts of the universe's story that are still being written. The imbalance between matter and antimatter is one such clue. It is not a contradiction. It is a feature waiting to be understood more deeply. And antimatter, by existing so faithfully within the known rules, frames that feature clearly. It narrows the question. It tells physicists exactly where to look. In that sense, antimatter is not a mystery object. It is a guide. It directs attention toward the early universe, toward symmetry, breaking, toward subtle processes that unfolded when everything was closer together and far more energetic than it is now. Those processes left behind a universe that feels stable and calm. But that calm is the result of ancient activity, frozen into structure. Antimatter preserves memory of that activity, not in the way a fossil preserves shape, but in the way a rule preserves history. The rules that allow antimatter are the same rules that allowed the universe to become what it is. And so, antimatter remains present, even when it is absent. It is present in equations, in experiments, in the logic of the universe. It is present as a possibility always allowed, even if rarely realized. This quiet presence gives physics a sense of completeness. It shows that the universe did not stop halfway. It explored its options. It allowed symmetry. It allowed reversal. It allowed counterparts. And then, through tiny differences amplified by time, it arrived here. Antimatter does not challenge that arrival. It explains it. It stands as evidence that the universe is not built from arbitrary choices, but from deep consistency. That what exists now is grounded in what could have existed, and that understanding reality means understanding both what remains and what nearly did. And in that understanding, antimatter settles into place, not as something exotic or distant, but as a natural, inevitable part of the same quiet framework that governs everything else, from the smallest particle to the broad sweep of cosmic history, all unfolding according to rules that are patient, balanced, and remarkably kind to those willing to look closely. Antimatter also offers a quiet way of understanding why physics places such importance on symmetry, even when symmetry is not exact. Symmetry is not a promise that everything will be evenly distributed. It is a promise that the rules themselves do not favor one outcome over another without reason. Antimatter exists because the rules allow it. Matter dominates because history unfolded a certain way. This distinction helps separate laws from outcomes. Laws describe what can happen. Outcomes describe what did happen. Antimatter belongs fully to the first category. Its scarcity belongs to the second. Once this separation becomes clear, the universe starts to feel less arbitrary. There is no sense that something went wrong or that antimatter failed to survive. There is only the sense that one of many allowed paths became the one that persisted. The others remain encoded in the rules, waiting to be expressed under the right conditions. Those conditions still arise, briefly, here and there. In the heart of particle accelerators, energy is concentrated so tightly that matter and antimatter appear together again, just as they did in the early universe. For a moment, symmetry returns. Then the environment reasserts itself, and annihilation follows. The universe moves on, carrying the imprint of that brief balance in the form of light. This pattern repeats across scales. Balance appears locally. History decides globally. Antimatter fits neatly into that rhythm. There is also something revealing about how antimatter challenges intuition without breaking it. It asks you to accept that opposite properties can coexist within the same framework, that flipping a sign does not require reinventing reality. Once that idea settles in, many other concepts in physics become easier to approach. Charge, spin, parity, even time itself start to feel more flexible, less absolute, without becoming vague. This flexibility is not looseness. It is precision expressed in a broader space of possibilities. Antimatter sharpens this sense of precision. It shows that the universe does not rely on rough approximations. It tracks details carefully. It remembers signs. It preserves balances. And when something changes, it changes according to clear rules. That clarity is especially evident in how antimatter behaves under measurement. When a positron moves through a magnetic field, its path curves exactly as predicted. When an antiproton is trapped, its motion matches calculations down to remarkable precision. There is no hint of chaos, no sense of hidden instability, just quiet agreement between theory and observation. This agreement builds trust not only in antimatter, but in the methods used to study it. It shows that even when dealing with rare and fleeting phenomena, careful reasoning and careful measurement can still reach something solid. For someone new to these ideas, this can be reassuring. It suggests that physics is not a collection of disconnected surprises. It is a coherent way of listening to nature, one that remains reliable even at its most abstract edges. Antimatter also invites a deeper appreciation of how little of reality is made of substance in the everyday sense. Matter itself is mostly empty space, structured by forces and fields. Antimatter shares this same architecture. The difference is not in how much stuff there is, but in how properties align. Once this becomes familiar, the word made of begins to feel different. Antimatter is not made of anti-atoms in the way a table is made of wood. It is made of arrangements, of relationships, of fields expressing themselves in a particular configuration. Matter is the same. This shift in meaning is subtle but important. It moves understanding away from objects and toward patterns. And patterns, once recognized, can be followed wherever they appear. That is why antimatter does not feel isolated from the rest of physics. It connects naturally to ideas about energy, fields, symmetry, and conservation. It reinforces them rather than challenging them. Even the mystery surrounding antimatter's scarcity strengthens this coherence. The mystery is not that antimatter exists. The mystery is that matter survived. That survival points toward processes that are small, delicate, and deeply woven into the fabric of physical law. Those processes are still being explored, not with urgency, but with care. Experiments are refined. Measurements improve. The picture sharpens slowly. Each new result narrows the space of possibilities, making the remaining questions more focused. Throughout this process, antimatter remains steady. It does not complicate the story. It anchors it. It anchors it by showing that the universe is not lopsided by accident. That asymmetry, when it appears, has structure. It has rules. It has limits. Antimatter defines those limits by contrast, and in doing so, it offers a calm perspective on existence itself. Everything familiar rests on something almost symmetrical. Stability rests on near balance. Presence rests on near absence. Antimatter embodies that nearness. It is the almost that never quite vanished, the counterpart that still appears whenever energy allows. The reminder that reality could have unfolded differently, and that the difference between what is and what might have been can be extraordinarily small. This does not make reality feel fragile. It makes it feel precise. It suggests that the universe is not held together by force alone, but by careful accounting, by rules that leave little room for ambiguity. Antimatter is part of that accounting. It ensures that equations close properly, that conservation laws hold, that symmetry is respected even when outcomes diverge. And because of that, antimatter does not stand apart from understanding. It deepens it. It adds context. It reveals structure that might otherwise remain hidden beneath the familiarity of matter. In the end, antimatter is less about opposition and more about completeness. It completes the logic of physics. It completes the story of the early universe. It completes the sense that reality, at its deepest level, is not chaotic or improvised, but carefully constructed, allowing just enough imbalance to let something enduring take shape. And that enduring shape, the one experienced as matter, carries antimatter within its logic, within its equations, within its origin, quietly, faithfully, as part of the same underlying order that continues to unfold, moment by moment, whether or not it is noticed. There is a point where the idea no longer needs to be named to remain present. Once the structure is understood, it can sit quietly beneath the surface, shaping everything without calling attention to itself. From here, the mirror counterpart does not need to be announced each time. Its role is already clear. What matters now is how this mirror sharpens the meaning of matter itself. Ordinary particles feel stable not because they are immutable, but because they occupy a long-lived arrangement that the universe happens to favor under current conditions. Stability is not permanence. It is endurance within a particular environment. The reversed counterparts follow the same rules, but they are less compatible with their surroundings, and compatibility is everything. This idea of compatibility runs through physics in many forms. Stars burn because nuclear reactions are favorable under immense pressure and heat. Atoms hold together because electromagnetic forces balance motion. Even life persists because the chemistry settles into self-sustaining cycles. None of these outcomes are guaranteed by the laws alone. They emerge because circumstances allow them to persist. The same is true here. The mirrored particles are not less real. They are less supported by the present universe, and that distinction is subtle but profound. In regions where conditions briefly resemble those of the early cosmos, balance returns. High-energy environments allow pairs to appear together again, briefly restoring symmetry. These moments are fleeting, but they are enough to confirm that nothing fundamental has changed. The rules still permit both orientations. History simply leans one way. This leaning does not feel dramatic when examined closely. There is no cosmic force pushing one version away. There is only a small statistical preference amplified by time. Billions of years can turn a whisper into a world. This amplification is one of the quiet powers of the universe. Tiny differences, repeated over immense durations, shape everything. Mountains rise, galaxies form. One version of matter remains while its counterpart fades. Not because it was weaker, but because chance and law intersected just so. Understanding this removes the need for drama. There is no villain, no failure, no missing piece in the everyday sense. There is only a system that followed its rules faithfully and arrived at one of many allowed outcomes. This perspective also softens the idea of rarity. Something can be rare and still be essential. Oxygen is rare in the universe compared to hydrogen, yet it shapes planets and life profoundly. The mirror particles are rare here, but they are essential to understanding why anything exists at all. Without them, the story would be incomplete. They serve as a reference point, a baseline, a way of checking that the equations describing reality are not biased or incomplete. Their existence confirms that the framework is broad enough to allow alternatives, even if those alternatives do not persist. This broadness is one of the strengths of physics. It does not demand that the universe be simple in its outcomes. It only demands that the rules be consistent. Complexity emerges naturally from consistency combined with time. From this angle, the universe feels less like a machine and more like a long experiment, one that began with symmetry and gradually explored what happens when symmetry is gently disturbed. The results are not rushed. They unfold patiently, layer by layer. The mirror counterpart is part of that exploration. It is evidence that the universe did not lock itself into a single path from the start. It allowed options. It allowed reversals. It allowed balance. And then, through minute differences, it allowed one option to dominate. This dominance should not be mistaken for inevitability. It is simply the outcome that endured. What remains now is a universe that feels calm and predictable at human scales, yet still carries within it the logic of its more symmetrical past. That logic shows up whenever energy rises high enough, whenever conditions briefly resemble those early moments. The same patterns reappear, quietly confirming that nothing fundamental has been lost. This continuity across time is one of the most reassuring aspects of physics. The universe does not forget its rules. It does not abandon possibilities. It only expresses them differently as circumstances change. And this is where the deeper comfort lies. The world you experience is not fragile because it rests on balance. It is resilient because the balance was almost perfect. The small difference that allowed matter to remain was enough, but only just. That narrow margin lends existence a kind of precision that feels almost intentional, though it arises entirely from natural law. The mirror particles remind us of that margin. They are the almost, the near symmetry, the possibility that stayed possible, even as it became rare. They also remind us that understanding does not require constant novelty. Once an idea is internalized, it can fade into the background and continue doing its work quietly. The best theories are like that. They do not demand attention. They support everything else. In this way, the mirror concept becomes less of a topic and more of a lens. Through it, matter looks less like a default and more like a survivor. Stability looks less like a given and more like a long-maintained condition. Existence looks less like a certainty and more like a sustained outcome. And none of this diminishes the reality of the world. It enriches it. It adds depth without adding confusion. It shows that what is familiar rests on structures that are elegant, restrained, and deeply coherent. That coherence does not shout. It does not need to. It holds quietly, patiently, allowing galaxies to drift, atoms to bind, and understanding to deepen slowly, without urgency. And in that quiet holding, the mirror remains present, not as a repeated word, but as an idea woven so thoroughly into the fabric of reality that it no longer needs to be named to be felt. There is a quiet shift that happens once the mirror idea no longer feels external. Instead of picturing two opposing kinds of substance, it begins to feel like a single framework expressing itself in complementary ways. What remains most striking is how little extra effort the universe expends to allow this. The same laws, the same constants, the same background structure quietly support both expressions without conflict. From this view, matter itself starts to look less like a default state and more like a particular alignment that happened to last. Its stability comes not from dominance, but from circumstance. The surrounding universe favors it, supports it, allows it to persist. Change the surroundings and persistence would look very different. This perspective is common in physics, even if it is rarely stated directly. Phases of matter change when conditions change. Ice becomes water. Water becomes vapor. Nothing fundamental is lost in the transition. Only the arrangement shifts. The mirror counterparts of familiar particles follow the same principle. They are not forbidden. They are simply out of phase with the current environment. There is something calming in that realization. It means the universe is not rigid. It adapts. It explores. It permits variation without losing coherence. The same rules govern everything, whether it endures or fades quickly. That coherence shows up especially clearly when energy is considered. Energy does not distinguish between one orientation and another. It flows into fields, excites them, reshapes them. What emerges depends on what combinations are allowed and what combinations can survive. The mirror configurations emerge naturally wherever energy is dense enough. They do not struggle to appear. They only struggle to remain. This struggle is quiet and impersonal. It has nothing to do with conflict. It is simply the result of interaction. When two complementary excitations meet, they transform into something simpler. The universe prefers simplicity when given the chance. Light carries energy away efficiently. Complexity collapses gently back into radiation. This preference for simplicity is not moral or intentional. It is mathematical, and it applies equally to everything. Understanding this can soften the emotional weight people sometimes attach to these ideas. There is no sense of loss when mirror particles vanish. They fulfill their role. They appear when conditions allow, and they leave when conditions change. Nothing resists this process, because nothing needs to. From this angle, existence itself begins to look like a balance between expression and return. Patterns arise, persist for a time, and dissolve. Some patterns last longer than others. Matter happens to be one of the longer-lasting ones. What makes this particularly interesting is that the long-lasting patterns still carry within them the logic of the short-lived ones. The rules that allow brief expressions also govern enduring structures. The difference is not in the rules, but in the stability of the outcome. This idea echoes across physics. Stars shine because they have found a long-lasting balance between gravity and pressure. Eventually, that balance shifts. Atoms are stable because forces and motion settle into equilibrium. Change the balance, and atoms ionize. Nothing about these processes is dramatic when viewed from the level of law. They are simply transitions between allowed states. The mirror counterparts fit neatly into this picture. They represent states that are allowed, but not favored here and now. Their rarity is a feature of the current universe, not a flaw in the framework. This can lead to a deeper appreciation of how history shapes reality. The universe has a memory, not in the sense of recollection, but in the sense that past conditions influence what remains possible. The early imbalance set a direction. Everything since has unfolded along that direction, even though the rules themselves remain impartial. That impartiality is one of the most reassuring aspects of physics. It suggests that understanding does not depend on where you stand or what you observe. The same principles apply everywhere. They applied in the early universe. They apply now. They will apply long after current structures fade. The mirror configurations are part of that universality. They are not relics in the sense of outdated features. They are living possibilities, expressed whenever conditions permit. Their continued appearance in experiments and cosmic events confirms that the universe has not lost its symmetry. It has simply expressed it unevenly. This uneven expression is subtle enough that it invites humility. It reminds us that large outcomes can arise from small differences, and that understanding those differences requires patience rather than force. The universe does not reveal its deepest preferences easily. It hints. It allows careful measurement. It rewards attention over time. And attention, once sustained, changes how familiar things feel. Matter stops feeling like the only option. It becomes one option that succeeded. Stability stops feeling guaranteed. It becomes something maintained. Existence itself stops feeling inevitable. It becomes something that continues because conditions still support it. This does not make the world feel precarious. It makes it feel precise. Every structure rests on balances that are actively maintained by the laws of physics. Nothing is sloppy. Nothing is accidental in the casual sense. Even outcomes shaped by chance unfold within strict boundaries. The mirror idea sharpens this sense of boundary. It shows exactly how far symmetry extends and exactly where it bends. It shows that the universe is willing to allow almost perfect balance, then deviate just enough to let complexity grow. That deviation is small enough to be almost invisible, yet powerful enough to shape everything. This contrast between scale and consequence is one of the most striking features of modern physics. Tiny asymmetries matter. Slight preferences matter. Over time, they matter enormously. The mirror particles stand as evidence of that truth. They embody the road not taken, preserved within the equations themselves. They show that the universe had options, and that the option it chose was not forced, but emerged naturally from subtle conditions. Seeing this does not demand awe. It invites quiet respect. Respect for a system that is neither fragile nor rigid, but balanced. Respect for laws that allow freedom without chaos. Respect for a universe that unfolds patiently, without urgency. And within that unfolding, the mirror remains present as a silent companion to everything familiar, not competing, not opposing, simply existing wherever it is allowed, then stepping aside when conditions no longer support it. That stepping aside is not disappearance, it is transformation. Energy continues, fields remain, possibility stays intact. This continuity is perhaps the most comforting realization of all. Nothing truly ends. It changes form, patterns shift, expressions come and go. The underlying structure persists, steady and impartial. The mirror idea fits seamlessly into that structure. It does not demand special attention. It does not need repetition. Once understood, it settles into the background, quietly supporting a deeper sense of coherence. And from that coherence, understanding grows naturally. Not through effort or strain, but through familiarity. The universe begins to feel less like a puzzle and more like a long, patient explanation, unfolding at its own pace, inviting understanding not by force, but by allowing space for ideas to settle gently into place. There is also a gentle way this idea reshapes how time feels in physics. The mirror relationship is not just about properties like charge or orientation. It touches time itself, not in a dramatic sense, but in the way equations remain valid whether processes unfold forward or backward. Many of the fundamental laws do not care which direction time points. They describe relationships, not sequences. What changes with time is not the law, but the story the universe happens to tell. This is where the early imbalance becomes especially meaningful. At the beginning, the universe was hot, dense, and fast-moving. Processes unfolded rapidly. Interactions that are now rare were once common. In that environment, tiny asymmetries mattered. They did not matter because they were large, but because everything was happening all at once. A slight preference, repeated across countless interactions, became decisive. As the universe expanded and cooled, those early decisions became locked in. The pace slowed. Conditions changed. What was once reversible became effectively one-directional. Not because the rules forbade reversal, but because the environment no longer supported it. Time gained an arrow, not from law, but from circumstance. The mirror idea fits naturally into this picture. It belongs to the realm where reversibility is still allowed, where balance can still be restored briefly under the right conditions. That realm has not vanished. It still appears in moments of high energy, in controlled experiments, in distant astrophysical events. It is quieter now, but it is still there. This connection to time helps explain why these ideas feel subtle rather than dramatic. They are not about sudden changes or sharp boundaries. They are about transitions, about how behavior shifts gradually as conditions evolve. Physics at its deepest level is often about continuity, not disruption. Continuity is what makes the universe intelligible. It allows understanding to accumulate. It allows simple principles to apply across wildly different scales. The same logic that governs fleeting particle interactions also governs the long-term evolution of galaxies. The mirror relationship bridges these scales, showing that what happens in the smallest moments is connected to what unfolds over billions of years. This connection can quietly change how existence itself feels. Instead of seeing the present as isolated, it becomes part of a long flow. The world around you carries within it the imprint of conditions that no longer exist, preserved not as memory, but as structure. The dominance of matter is one such imprint. The continued possibility of its mirror is another. Neither is more real than the other. One is simply more compatible with the present. Compatibility is an underappreciated concept in physics. Systems do not persist because they are correct. They persist because they fit. They fit their environment, their constraints, their available energy. Change the environment, and what fits changes too. This idea scales smoothly from the smallest to the largest systems. Chemical reactions proceed because energy differences favor certain outcomes. Stars form because gravity and pressure settle into balance. Patterns endure because they are supported. When support fades, patterns dissolve. The mirror configurations follow the same rule. They are fully allowed by the laws, but they are not supported for long in the current cosmic environment. That lack of support does not diminish their legitimacy. It simply limits their presence. Seeing this can gently dissolve the sense that reality is made only of what is common. Rarity becomes meaningful rather than marginal. Short-lived phenomena become informative rather than trivial. Even fleeting patterns can reveal deep truths about the rules that allow them. This is one reason physicists pay such close attention to things that barely persist. The shortest-lived particles, the rarest interactions, the most delicate asymmetries often carry the most information. They probe corners of the framework that everyday phenomena never reach. The mirror idea lives in those corners. It reveals how carefully the universe keeps track of properties, how strictly it enforces balance, how small deviations are permitted but never without structure. That structure brings a sense of calm. Even when outcomes surprise us, the underlying logic does not. It remains steady, patient, and precise. And precision does not mean rigidity. It means clarity. The rules are clear about what they allow. They do not promise symmetry in outcomes, only in possibility. They do not guarantee fairness in distribution, only consistency in law. This distinction becomes more comfortable the longer it is held. It removes the need to see the universe as biased or flawed. It replaces those ideas with a simpler picture. The universe allows many things. History determines which ones remain. From that view, the present moment feels less accidental and more contextual. It is not the only version that could have existed. It is the one that did. And understanding why it did requires looking not only at what remains, but at what almost did. The mirror concept preserves that almost. It keeps the alternative visible, not as a threat, but as a reference. It shows what symmetry looks like before history tips the balance. This reference is invaluable. Without it, the dominance of matter would feel arbitrary. With it, dominance feels earned by circumstance rather than granted by law. That subtle shift in perspective can be deeply settling. It frames reality as something that unfolded naturally, without favoritism or intent, guided by rules that are broad enough to allow variation and strict enough to maintain coherence. And coherence is what holds everything together. Not force, not will, but consistency applied patiently over time. The mirror idea does not disrupt that coherence, it reinforces it. It shows that even when outcomes diverge, the framework remains intact. That even when symmetry bends, it does so within well-defined limits. These limits are what make understanding possible. They give physics its quiet confidence. They allow unfamiliar ideas to be integrated rather than isolated. And so the mirror remains present, not as a repeated label, but as an underlying principle. It supports the sense that reality is not a collection of exceptions, but a unified system expressing itself differently under different conditions. That unity does not demand attention. It does not insist on explanation. It simply holds, allowing structures to form, dissolve, and form again, each time following the same patient logic. Within that holding, understanding grows naturally, not by chasing answers, but by noticing how familiar ideas connect, how patterns repeat, how differences emerge without breaking continuity. And in that noticing, the universe begins to feel less like something to solve and more like something to accompany, unfolding quietly, consistently, and with enough room for both what remains and what almost did, coexisting within the same deep and remarkably gentle order. There is a quiet clarity that emerges when the idea is allowed to rest without being named. The structure it points to continues doing its work beneath the surface, shaping understanding without needing to be called forward explicitly. At this point, the picture is no longer about a specific category of particles, but about how the universe permits alternatives while sustaining coherence. What becomes especially noticeable is how carefully physical law separates permission from prevalence. The rules are generous. They allow reversals, counterparts, and complementary forms. They do not rush to eliminate possibilities, but they are also precise. They place strict conditions on what can last. Endurance is not guaranteed by allowance. It is granted by fit. This distinction explains much of what feels puzzling at first glance. Why certain patterns fill the universe while others appear only briefly. Why some configurations dominate everyday experience while others remain confined to laboratories or distant cosmic events. The laws do not choose favorites. Circumstance does. Circumstance itself is shaped by earlier events. The universe did not reset its conditions after the first moments. It carried them forward. Temperature dropped. Density decreased. Expansion continued. With each change, certain processes slowed, others stopped, and some became effectively impossible without extreme intervention. Yet nothing fundamental was removed. The underlying permissions remained intact. The framework stayed open. Only the environment shifted. This is why high-energy experiments feel like time travel in a conceptual sense. They do not recreate the past exactly, but they momentarily restore conditions where forgotten possibilities can surface again. In those moments, symmetry reappears. Complementary forms arise together. The universe briefly revisits an earlier balance, then moves on. These moments are fleeting, but they are deeply informative. They confirm that the framework has not changed. The same relationships hold. The same balances apply. What differs is how long those balances can be maintained. This reveals something subtle about permanence. Permanence is not a property of things. It is a property of conditions. Change the conditions, and what appears permanent becomes temporary. Change them again, and new stabilities emerge. Physics is full of such transitions. Solid becomes liquid. Liquid becomes gas. Plasma forms under sufficient heat. None of these phases are more real than the others. They are expressions of the same underlying matter responding to different circumstances. The mirror configurations follow the same logic. They are phases that the universe can express, but does not sustain under present conditions. Their absence is not exclusion. It is a phase preference. Understanding this softens the feeling that something is missing. Nothing is missing. Everything permitted remains permitted. The universe simply expresses a subset of its possibilities most of the time. This subset happens to include atoms, chemistry, planets, and life. That outcome feels extraordinary, but it rests on conditions that were never guaranteed. It emerged from near balance, from differences small enough to be overlooked without careful measurement. Those differences are still being studied, not because the framework is in doubt, but because understanding how small effects produce large outcomes is one of the deepest challenges in science. It requires patience. It requires precision. It requires comfort with uncertainty. The mirror idea contributes to that comfort. It shows that uncertainty does not mean chaos. It means structure that has not yet been fully resolved. The rules are clear. The details are subtle. Subtlety is where physics becomes most interesting, not in dramatic forces or violent events, but in small deviations that accumulate quietly over time. The universe is shaped less by explosions than by persistence. Persistence is what allowed matter to remain. It is what allowed structure to form. It is what allows the present to exist at all. But persistence does not erase alternatives. It simply outlasts them. And the alternatives continue to exist as possibilities, ready to appear whenever conditions briefly allow. This coexistence of what lasts and what could last gives the universe depth. It prevents reality from feeling rigid or predetermined. It preserves a sense of openness, even within strict law. That openness is not randomness. It is constraint combined with freedom. The laws constrain what is possible. Circumstance determines what happens. Time amplifies small differences into lasting outcomes. From this angle, the universe feels less like a machine and more like a long, unfolding process, guided by rules that do not rush and do not revise themselves. They simply apply, everywhere, always. Within that application, patterns arise. Some fade quickly, some endure. None are arbitrary, all are lawful. The mirror idea reinforces this by showing that even what fades quickly is fully lawful. It belongs. It fits. It just does not persist here and now. This realization can bring a kind of intellectual calm. It removes the need to categorize phenomena as normal or abnormal. Everything is normal under the right conditions. What differs is how often those conditions occur. That calm extends to how questions are approached. Instead of asking why something exists at all, the more precise question becomes why it persists. And persistence is something physics understands well. It is about balance, feedback, and stability. Balance does not require equality. It requires compatibility. A slight imbalance can still be stable if it is self-sustaining. The early universe found such a state. Everything since has unfolded from it. The mirror configurations remain as markers of that near equality. They show how close the balance once was. They show that the universe did not need a dramatic push to tip one way. It needed only time. Time is the quiet multiplier. It turns small preferences into defining features. It turns rare events into shaping forces. It turns near symmetry into a world that feels one-sided. Yet the symmetry remains encoded. It has not been erased. It simply lies beneath the surface, waiting for conditions that allow it to show itself again. This layered structure of reality is one of its most reassuring features. Nothing is wasted. Nothing is discarded. Possibilities are not destroyed when they cease to dominate. They are preserved in law, and law in physics is not imposed. It is discovered. It describes what the universe consistently does, not what it intends. The mirror idea aligns perfectly with this. It is not a story added on top of observation. It emerges naturally from the way the universe behaves when examined carefully. That natural emergence is what gives it weight. It is not speculative. It is not decorative. It is structural. And once that structure is seen clearly, it no longer needs to be pointed out constantly. It becomes part of the background understanding, quietly informing how everything else is interpreted. From there, the world begins to feel subtly different. Familiar objects carry a sense of contingency. Stability feels earned rather than assumed. Existence feels supported by balance rather than guaranteed by necessity. This does not diminish meaning. It deepens it. It adds context. It connects the present moment to a vast history of conditions, interactions, and near misses that collectively made it possible. Within that context, understanding grows without effort. Ideas settle naturally. Connections form quietly. The universe reveals itself not as a puzzle-demanding solution, but as a system that becomes clearer the longer it is observed with patience and care. And in that clarity, the mirror remains present, not as a repeated name or emphasized concept, but as a silent assurance that reality is broader than what is seen, and that what is seen rests securely within a framework generous enough to allow alternatives, precise enough to sustain coherence, and calm enough to unfold without haste, moment by moment, according to rules that do not need to be announced to be trusted. There is a certain steadiness that comes from realizing how little the universe rushes. Even its most profound differences unfold slowly, guided by rules that never hurry and never revise themselves. Once that steadiness becomes familiar, the story no longer feels like a sequence of discoveries, but like a single, continuous explanation that has always been there, waiting to be noticed. At this depth, the picture is no longer about individual particles or rare laboratory events. It is about the character of physical law itself. The laws do not chase outcomes. They define relationships. They allow structures to arise, interact, persist, and dissolve, all without preference or intention. What remains visible is simply what fits longest within the environment those laws create. This is why the present universe feels so settled. Expansion has slowed interactions, temperatures have dropped, energy is spread thinly across vast distances. Under these conditions, only certain arrangements endure. Others appear briefly, then return to simpler forms. This is not exclusion. It is equilibrium reached through time. Time itself becomes easier to understand in this context. It is not an external force pushing things forward. It is a measure of how systems move through allowed states. When conditions change rapidly, time feels eventful. When conditions change slowly, time feels calm. The universe now is in a calm phase, not because activity has ceased, but because the most dramatic transformations are behind it. Yet the calm does not erase what came before. The early conditions are written into the structure of everything that exists. They are present not as memories, but as constraints and possibilities that still shape behavior. The dominance of matter is one such imprint. The continued allowance of its mirror counterpart is another. This coexistence of imprint and possibility is one of the most subtle aspects of reality. It shows that the universe does not discard its options when it moves on. It simply expresses them differently. The rules remain wide, even as outcomes narrow. Understanding this removes the need to see the present as fragile or precarious. Stability does not require exclusivity. It requires balance that can sustain itself. The current balance has done so for billions of years, not because it was guaranteed, but because it was sufficient. Sufficiency is a quiet concept in physics. It does not mean optimal. It does not mean inevitable. It means adequate to persist. Many arrangements are adequate for a time. Few remain adequate as conditions evolve. The ones that do are the ones that shape history. This way of thinking naturally extends beyond particles and into larger structures. Galaxies exist because gravity and expansion found a workable balance. Solar systems persist because orbital dynamics settled into stable patterns. Life arises where chemistry finds long-lived cycles. None of these outcomes were mandated. They emerged because they could endure. The mirror configurations follow the same principle. They are fully valid arrangements within the laws, but they do not endure under current conditions. Their fleeting nature does not diminish their importance. It highlights how selective endurance can be. Selective endurance does not imply choice or intent. It is simply the result of interactions playing out over time. Given enough time, even tiny preferences become decisive. Given enough space, rare events become inevitable somewhere. The universe is large enough and old enough for this to matter. This perspective brings a kind of intellectual relief. It removes the pressure to find dramatic explanations for every imbalance. Often, the explanation is simply time combined with law. Small effects, applied consistently, shape everything. That consistency is one of the most beautiful features of physics. The same equations apply whether something lasts a fraction of a second or billions of years. They do not adjust themselves based on scale or significance. They apply equally, impartially. This impartiality is what allows understanding to feel trustworthy. When a theory predicts both common and rare phenomena accurately, it earns confidence. The mirror counterpart is one of those rare phenomena that strengthens confidence precisely because it behaves exactly as expected. It confirms that the framework does not break under stress. It holds at extremes. It remains coherent even when pushed into unusual regimes. That robustness is not accidental. It reflects a deep alignment between mathematics and reality. Mathematics, in this sense, is not an invention layered on top of the universe. It is a language that mirrors the structure already there. The fact that it predicts complementary forms so reliably suggests that the universe itself is structured in a way that favors balance and consistency. Balance, however, does not mean stasis. It means dynamic stability. Forces pull and push, energies flow, patterns emerge and dissolve. The system remains coherent not because nothing changes, but because change itself is constrained. Those constraints are what allow long narratives to exist at all. Without them, nothing would persist long enough to be noticed. The universe would be a blur of transient events with no structure. The mirror idea reinforces how close reality is to that edge. It shows that the universe allows fleeting expressions right alongside enduring ones. It allows near symmetry and then permits slight deviation. It operates close to balance, not far from it. Operating close to balance has consequences. It means small changes matter. It means history matters. It means the present is shaped not just by law, but by sequence. Sequence is where time enters again, not as an abstract dimension, but as the ordering of events that amplifies some possibilities and suppresses others. Once an arrangement gains an advantage, even a tiny one, repetition does the rest. Repetition is powerful. Over countless interactions, preferences compound. What begins as a statistical quirk becomes a defining feature. This is not unique to particles. It appears everywhere in nature. Rivers carve valleys. Evolution shapes species. Markets trend. All are examples of small biases accumulating over time. The early imbalance between matter and its mirror follows this same logic. It did not need to be large. It only needed to exist. Time ensured that it mattered. Understanding this removes the temptation to look for dramatic mechanisms where none are required. It shifts focus toward subtle processes that operate persistently. These processes are harder to detect, but far more influential. Physics has become increasingly skilled at studying such subtlety. Instruments grow more sensitive. Measurements grow more precise. The ability to test near-perfect symmetry improves year by year. Each test refines understanding, even when it confirms expectations. Confirmation itself is valuable. It tells us that the foundation is sound. It allows unanswered questions to be framed more clearly. It narrows the search. The mirror counterpart plays a central role in this narrowing. It defines what symmetry looks like. It provides a reference against which deviation can be measured. Without it, imbalance would be harder to quantify. In this sense, rarity becomes a tool. What appears only briefly carries information that what persists does not. Fleeting phenomena probe regimes that stable structures never reach. They reveal how the rules behave under stress. This is why physics does not dismiss what is rare. It studies it carefully. It listens closely. It recognizes that brief appearances can illuminate deep structure. The mirror idea belongs to this category. It is not prominent in everyday life, but it is foundational in theory. It is not persistent, but it is essential. Once this is understood, it no longer needs emphasis. It becomes part of the background logic that supports everything else. Like gravity, it does its work quietly. That quiet support is what allows understanding to feel cumulative rather than fragmented. New ideas do not replace old ones. They integrate with them. The picture grows more complete without becoming more chaotic. This integration is one of the most satisfying aspects of learning physics. Concepts that once seemed isolated begin to connect. Patterns repeat across scales. Differences reveal underlying unity. At that point, the universe feels less like a collection of mysteries, and more like a single, coherent system expressing itself in many ways. Some expressions last, some pass quickly. All are lawful. The mirror configurations remind us of this lawfulness. They show that even what does not endure belongs fully to the same order as what does. They confirm that reality is not divided into normal and abnormal, but into persistent and transient. And transience, far from being insignificant, is often where the most revealing information lies. This recognition changes the tone of curiosity. It becomes calmer, less driven by surprise, more guided by coherence. The goal is no longer to uncover something shocking, but to see how everything fits. Fitting, in physics, is not about forcing ideas together. It is about allowing them to align naturally under shared principles. When alignment occurs, understanding feels effortless. The mirror idea aligns effortlessly with the rest of modern physics. It requires no special pleading. It introduces no contradictions. It settles into place quietly, like a missing piece that was always implied by the shape of the puzzle. Once in place, it allows the larger picture to be seen more clearly. The universe emerges as a system that values consistency over outcome, balance over dominance, and patience over urgency. Within that system, existence is not guaranteed, but it is explainable. It arises from near balance, maintained by law, shaped by time. That explanation does not diminish wonder. It refines it. It replaces vague awe with quiet appreciation. It shows that the universe is remarkable not because it is chaotic or arbitrary, but because it is restrained, precise, and generous enough to allow complexity to grow from simplicity. And in that generosity, the mirror remains ever present as a possibility, a reference, a reminder of how close the universe came to another outcome, and how delicately the present one is supported. Nothing about this needs emphasis. Nothing needs repetition. The idea has already settled. What remains is a sense of coherence that does not demand attention, but rewards it. A sense that the universe, in allowing both persistence and transience, has built a reality that is not only understandable, but quietly elegant, unfolding without hurry, according to rules that remain faithful to themselves, moment after moment, across scales so vast and small that even the rarest expressions find their place within the same enduring, patient order. There is a moment in any long understanding when the pieces stop arriving and instead begin to rest. Nothing new needs to be introduced. The structure is already complete. What changes is the way it is held. At this stage, the universe no longer feels like it is asking to be explained. It feels like it is allowing itself to be seen. What remains most striking is how restrained everything is. The laws that allow existence do not strain or dramatize their outcomes. They permit balance. They permit reversal. They permit alternatives. And then they wait. Time does the rest. Matter persists not because it defeated its counterpart, but because it remained compatible as conditions cooled and thinned. The universe did not erase symmetry. It carried it forward quietly, even as one expression became dominant. The mirror remains written into the equations, preserved not as memory, but as structure. This preservation is important. It tells us that the present is not the whole story, only the visible chapter. Beneath it lies a deeper consistency that has never changed, even as everything else has. When physics reaches this level, it stops feeling like a hunt for answers and starts feeling like a listening practice. The universe speaks softly. It reveals itself through patience, through repetition, through rules that never raise their voice. Nothing here is accidental, but nothing is forced either. The balance is gentle. The differences are slight. The outcomes are immense. That is perhaps the quietest lesson of all. Existence is not built on extremes. It is built on margins, on near equality, on just enough difference to let something remain. Those margins are still present now, woven into every interaction. They are why atoms hold, why stars burn steadily instead of all at once, why the universe evolves rather than collapses or freezes completely. they are also why understanding feels possible. The same restraint that governs particles governs knowledge. Nothing has to be grasped all at once. Clarity emerges gradually as ideas find their place and stop needing attention. At this point, the mirror no longer feels like an object of focus. It feels like a part of the background fabric, supporting everything else without being noticed. That is how fundamental ideas behave once they are understood. They disappear into usefulness. What is left is a sense of coherence that does not demand effort. The universe feels less like a collection of phenomena and more like a single, continuous process, unfolding calmly, without urgency, according to rules that are consistent enough to trust. And within that trust, curiosity softens. It becomes less about seeking and more about accompanying, less about uncovering and more about noticing. The present moment, then, feels gently suspended within a much larger continuity. Everything solid rests on balances that were almost different. Everything familiar is supported by possibilities that remain allowed, even if they are rarely expressed. Nothing needs to be emphasized anymore. Nothing needs repetition. The understanding has already settled. What remains is quiet alignment, a sense that reality is not brittle, not arbitrary, not chaotic, but carefully permissive, patiently selective, and deeply consistent across scales far beyond immediate experience. And in that consistency, the universe feels less distant, not because it is simple, but because it is coherent. Not because it reveals everything, but because what it does reveal fits together without strain. That coherence continues whether it is observed or not. It held in the beginning. It holds now. It will hold long after present structures dissolve back into simpler forms. Nothing is lost in that return. The rules remain. The possibilities remain. The mirror remains, not as a thing to search for, but as a quiet assurance that reality is broader than what persists and steadier than what changes. From here, there is nowhere in particular to go. The framework is complete. The universe continues. And understanding, having arrived where it needs to be, is free to rest within it.